Today we are going to learn Fermi's golden rule. Fermi's golden rule is a formula that describes the transition rate from one energy eigenstate of a quantum system to a group of energy eigenstates which are in continuum as a result of weak perturbation. It could happen that during the course of transition, the atom or electron get excited to final states, and that final state is a part of continuum. That is, the final state is not a single well defined state, but it is a collection of large number of states and whose energy levels or energy values are so close by. So, the transition occurs to a continuum of final states. And today we are going to discuss about the transition rate if the transition occur to a continuum of final states. So, using the time dependent perturbation theory, we have the first order transition probability for the transition from an initial state I to a final state F is given by Pi f of t is modulus of Cf1 of t the whole square, where Cf1 of t is defined as modulus of minus I by h bar integral 0 to t V fi of t prime e raised to I omega fi t prime dt prime, where V fi of t prime is the perturbing potential and it is the ith matrix element of the perturbing potential, and omega fi is the angular frequency difference, that is omega fi equals Ef minus Ei by h bar. This is the case of transition probability for the transition from an initial state I to final state F. Here in this case, we have not a single well defined final states. We have a collection of large number of states whose energy values are so close by. That is, instead of a single well defined state, we have a collection of large number of states, or we have a continuum of final states. So, here we have to consider the density of final states. If rho of E denote the density of final states. Density of final state means number of states per unit energy range. So, if this is Ef, this level corresponds to energy level Ef, and this level corresponds to energy level Ef plus Def. So, if rho of Ef is the density of final states, then the number of states in the energy interval between Ef and Ef plus Def is given by rho of Ef into Def. That is, this is the number of states in the energy interval Def. So, how we got the total probability? The total probability is obtained as sum over all such final states. Total probability is obtained as sum over all such final states. That is integral over 0 to integral over all such final states. Here the integration is over the energy range. So, we do not put the energy limit here now. So, integral over modulus of Cf1 of t the whole square rho of Ef into Def, where rho of Ef into Def when multiplied with the transition probability from the initial state I to final state F and integrated over the whole available final energy states, we get the total probability. So, for a constant perturbation, if we wait for a long enough time, that is, if as t tending to infinity, we have Cf1 of t modulus square as 2 pi t by h bar modulus of Vfi prime square delta of Ef minus Ei. Here Vfi prime is the constant perturbation which is independent of time, and this is the Dirac delta function, delta of Ef minus Ei. This is the transition probability if we wait for a long enough time in the case of a constant perturbation. So, we substitute the value of modulus of Cf1 of t the whole square into the equation number 1. So, we got P equals integral over 2 pi t by h bar modulus of Vfi prime square delta of Ef minus Ei rho of E into d. It is correct if we not, since this is the integration over all the energy levels, it is more correct if we put the variable not as Ef, just like E. So, here it is rho of E into d. Now, if we integrate over this, due to this Dirac delta function, if Ef equals Ei, this term exists. For all other values of energy, that is if Ef not equals Ei, this term vanishes. So, this integral over the energy range exists only if Ef equals Ei. So, this integral vanishes and we got 2 pi t by h bar modulus of Vfi prime square rho of Ef. Here it can be rho of Ef or rho of Ei, since it exists only if Ef equals Ei. So, we have the total probability. Now, the rate of transition or transition probability per unit time is obtained as R is equal transition probability per unit time, which is equals 2 pi by h bar modulus of Vfi prime square rho of Ef. That is, the transition rate is independent of time. Here we consider the constant perturbation, and in the constant perturbation we consider the case if we are waiting for a long enough time. The transition rate is independent of time. This relation is known as Fermi's golden rule. That is, the Fermi's golden rule is the transition rate is independent of time in the case of a constant perturbation if we wait for a long enough time. Thank you.